Electric fields may originate from charged objects, as we can see. And now consider this test charge Q. Then the electric force exerted on this test charge due to this charge appears as follows, and is equal to 1 over 4 pi by the permittivity of free space by the product of the two charges on the squared distance between them, as we've seen. So this electric force acts to repel this test charge. So therefore the electric field due to a charged object Q is equal to the ratio of the electric force that's exerted on the test charge at this point to the charge of the test charge, which in this case is Q. So therefore our electric field due to this charged object Q is written as follows, and is independent of the test charge. And a test charge is a point charge that has a small enough magnitude such that its presence does not significantly affect the electric field in its vicinity. So as we can see, given that the force is inversely proportional to the square of the radial distance between the two charges, then the electric field has the highest intensity near the charged object, and it drops off according to this inverse proportionality of the squared distance to the test charge. So we can see that the electric field has the highest intensity where these lines are more dense, and where the electric field lines become less dense, the electric field is weaker. So the electric field points away from isolated positive charges, which we can see over here, and if we had a negative charge, then the electric field will point towards it. And the electric force exerted on a positive test charge by an electric field, as we can see, is in the same direction as the electric field. So if we had a negative test charge over here that has a magnitude of 3Q, then the electric force exerted on this test charge points in the opposite direction as the electric field. And therefore, the electric force on this test charge is equal to minus 3Q multiplied by the electric field due to charge Q. So effectively we can place a test charge anywhere in this electric field and calculate the electric force exerted on it as follows. The electric field is a vector quantity that can be represented in space using vector field maps as shown. So as we can see, the vectors in the vicinity of the positive charge point away from it, and near the negative charge they point towards it. So here we have an electric field map for a dipole, where the dipole is two equal and opposite charges. Now the net electric field at a given location is the vector sum of the individual electric fields created by nearby charged objects. So for example, if we place a test charge at this point, then the electric field due to the positive charge acts away from the positive charge, and the electric field due to the negative charge acts towards the negative charge at this point. So if we superimpose these two vectors, we get the net electric field at this point. And similarly, if we place a test charge at this point, the electric field due to the positive charge points away from it, and is less intense than at this point over here, as we can see, because the test charge is further from these charges. And here the electric field due to the negative charge points towards it, so we can sum up these electric field vectors using the parallelogram rule of vector addition, and we get the net electric field at this point, which points to the right. Now given that electric field maps use vectors to depict the magnitude and direction of the electric field at many locations in a given region, electric field line diagrams can be drawn, which are simplified models of electric field maps. And they can be used to determine the relative magnitude and direction of the electric field at any position in the diagram. So for example here, the electric field line diagram is more dense where the electric field is stronger. And it's more dense between a positive and negative charge compared to this point up here, for example. And if we place a test charge at this point, we'll recall that the electrostatic force is equal to the charge by the electric field. So if the charge is positive, then the force on a charge is tangent to the electric field line at this point and points in the direction of the electric field. And if we place a negative test charge, for example, then the electric force still acts tangent to the electric field line at this point, but it acts against the electric field. The following static charges with a charge magnitude Q are positioned in a square configuration at a distance d from each other. Write an equation for the force exerted by charge 4 on charge 1. So we take our positive direction vector from charge 4, and we know that the force exerted by charge 4 on charge 1 is attractive, because these are opposite charges. So therefore for part A, we can write the electrostatic force as 1 over 4 pi by the permittivity of free space, and that's multiplied by the product of the two charges, so that will be minus Q by Q, so we get a negative here, over the squared distance between the charges. And that's multiplied by the unit vector pointing in a direction from charge 4 to 1. So as we can see, the electric force points in the opposite direction to the unit vector. Now part B asks us to determine the magnitude and direction of the electric field in the middle of the square. So suppose we place a test charge in the middle here, then this test charge is going to have an equal distance to all of those charges. And the positive charges have an electric field that points away from them. So this will be the electric field due to charge 4, and this one here is due to charge 2. And charge 1 has an electric field pointing towards it. And similarly for charge 3, because they're negative charges. So therefore, these two vectors will cancel each other out, and so will these two vectors, because the charges all have the same magnitude according to the problem. So therefore the net electric field in the middle of the square is 0. And note that it's a vector. Now part C asks us to determine the magnitude and direction of the electric field midway between charge 1 and 2. So let's make room over here. So the electric field points away from charge 4 and towards charge 3 and towards charge 1 and away from charge 2. So the magnitude of the electric field due to charge 4 is smaller than that due to charge 1 and 2, because the charge is further away from this point. And similarly, the electric field due to charge 3 points in this direction and has the same magnitude as the electric field of charge 4. And now we can use a bit of trigonometry to superimpose these electric fields. So if we take this as our angle theta, and if we take our positive direction pointing to the right, so we have the electric field component in the horizontal direction is minus E4 cosine theta plus E3 cosine theta. So given that E4 is equal to E3, these cancel, and the electric field component in the horizontal direction is 0. Now in the vertical direction, and taking the positive direction as upwards, we have E1 plus E2 and minus E3 sine theta. So we're taking the vertical component of this electric field vector. and similarly for E4. So given that E1 is equal to E2, because the two charges are at the same distance from this point, we can write this as 2E1. And similarly, the magnitude of the electric field due to charge 3 and 4 is the same. So we have minus 2 E3 sine theta. And by geometry, sine theta is the opposite, which is d on 2, on the hypotenuse. So we have sine theta is d on 2 over the square root of d squared plus d on 2 squared. So if we take d out of the square root, these d's are going to cancel. And doing some algebra, you'll get sine theta is 1 on root 5. And now we can substitute for E1, E3 and sine theta. So we have EY is 2 by 1 over 4 pi by the permittivity of free space, which will factor out. And E1 is the magnitude of the charge on the square distance from this point to the charge, which is d on 2 squared. And then minus E3, so the charge magnitude is again Q, over this distance to the charge. So the squared distance is d squared plus d on 2 squared by Pythagoras' theorem. And that's multiplied by sine theta, which is 1 on root 5. And let's simplify this a bit further. So we have 1 over 2 pi epsilon naught, and we'll also factor out the charge Q, and we'll also factor out d squared. So we have the reciprocal of 1 on 4, which is 4, and minus, so in the denominator we have 1 plus 1 on 4, which is 5 on 4. So taking the reciprocal, we have 4 in the numerator and 5 root 5 in the denominator. So given that this value is positive and the horizontal electric field component is 0, then this here is also the magnitude of the net electric field at this point. And the electric field is simply E by the unit vector in the vertical direction. So as we can see, this value is positive and the net electric field points upwards. When in electrostatic equilibrium, the excess charge of a conductor is distributed on the surface of the conductor. So for example, a metal conductor consists of metallic bonds where the electrons are free to move around. So if we take a section out of this conductor, we have the electrons distributed on the outer surface to get as far away from each other as possible. So we can visualize here that the electric fields, due to these charge carriers being the electrons, will cancel each other out. And therefore the electric field inside the conductor is 0. Now at the surface of the charged conductor, the electric field is perpendicular to the surface, as we can see. And this is also true for non-spherical conductors, which we'll look at later on. Now the electric field outside an isolated sphere with a spherically symmetric charge distribution is the same as the electric field due to a point charge with the same net charge as the sphere. And this equivalent point charge is located at the center of the sphere. Now for an insulator, being glass for example, the electrons are restricted to the covalent bonds between the molecules to form this covalent network solid structure. So therefore if we transfer electrons to this insulator, they're going to get trapped in the molecular structure of the solid, given that the electrons in the covalent bonds are restricted. So under electrostatic conditions, when these charges stop moving, the excess charge of the insulator is distributed throughout the interior of the insulator, and you'll also have the excess charge residing on the surface. So therefore the electric field within the insulator may have a non-zero value. And we'll look at these different charge distributions, including charge density functions, when we go through Gauss's law.